Good morning once again and welcome back to the lecture on distribution theory and Source spaces. So, in the last lecture we are discussing we have discussed many examples, and in the last example we are discussing about the Dirichlet functional. So, let me go through quickly once again about that one. So, we have introduced this functional f of v equal to half of integral of grade v square, and then we were trying to find the minimization problem, finding a u in an appropriate space x such that f of u is equal to minimum of f of v. So, you already know about how to deal with any minimization problem. The moment you have a minimization problem, one of the approach is to look for a minimizing sequence, and then minimizing sequence exists because the infimum is finite, and then Fn equal to alpha. The next step of finding is that you want to derive the convergence sequence. So, one of the, since C1 omega is given with a C1 norm, which is a supernorm of the functions and its derivatives, you look for, try to get estimates on that. But what I remarked is that where do you come from this example estimates? The estimates has to come from the minimization problem. The minimization problem is basically is integral of grade v square. So, you can expect only estimates with respect to grade v square. You cannot expect estimates with respect to supernorm. So, if you have an estimates with respect to supernorms, yes, of course, then you may be able to get uniform convergence, and with the uniform convergence you can apply Arcel's-Cowley theorem, etc. So, this fact of studying this minimization of the Dirichlet functional, many people including Levy observed that it has to need to work with C1 of omega bar with an integral norm. Okay. So, what we have discussed is so the question is that what is this space? Okay. We cannot easily understand. Of course, given any space, with that you can find the completion, you can find completion. Okay. The completion means completion consists of equivalent classes, you see, equivalent classes. So, how do we understand the equivalent classes? That is a question. How do we understand equivalent classes? Equivalent classes. In this let me just do a slight digression. You are already familiar with that. Look at this E of AB. I am sure you will heard about this one, CC01 if you want that. And look at a norm defined on C1 and integral. You know that C01 is given by the supernorm. With respect to that supernorm, it is complete. But if you are defining a one norm, integral of modulus of ft dt 0 to 1 dt. So, what is the completion of this one? Completion of this is the same situation we are facing now, C01 with respect to this one norm. So, you are interested in looking at that C01. How do you understand? Again, it is an equivalence classes, and this is the remarkable theory of Lebesgue measure theory. You see, Lebesgue measure theory and mesh integration. So, you understand certain completion, you may need to develop new theories, and this completion is nothing but your L1 of AB. You see, the one of the important concept is the almost everywhere concept in that almost everywhere concept. So, when you look for completion of this space now, you may end up functions, the completion may be, and that is precisely the Sobolev spaces you are going to see. The H1 spaces later you will see the first order kind of Sobolev spaces are nothing but this completion. The problem is that when you look at the completion, and even if after identifying the functions, identification itself involves a way of new theory, but you end up functions which are not smooth, functions which are not smooth, which are not smooth. Just like here, you have this function here, continuous function, but this consists of functions which need not be smooth, you see. So, but it is integrable. So, whatever property you are giving when you have a space and you have a norm, and if you look at the norm, a completion space basically it may preserve that property, it may not preserve the underlying property of C. For in this case, in C of A01, you have the underlying property of continuity, and that may not be preserved under completion. The property of the norm, that is integrability, is what is preserved here. So, the issue here is F is not smooth. So, if you start with so here your Fn is started with F all started with C1 of omega, but then you will have non smooth functions, but our underlying property is differentiability. Okay. F in C1 means it is differentiable, continuous and differentiable, and that property. So, how do we define differentiable derivative? So, that leads to the question, how do we define differentiability? Define differentiability. And that is what we are going to see. We are going to define a notion of weak derivative. You will see soon that. Okay. In a couple of lectures you will see formally, in the soon you will see more than that about this one. So, I will not get into too much about this one, anyway you are going to see all that. So, now I want to have one more example, very interesting example, example of Dirac delta. Please I request all of you, all the students who study, not to forget the examples. Oh sorry, it is not about the Dirac delta. Dirac delta function. In the beginning of 20th century, probably around the 1910s or 1920s, Paul Dirac, he was a physicist, Paul Dirac introduced a function, formally introduced delta function. What was he wanted? Some two things. He wanted delta x is equal to 0. This is what most of the books even now write it, but you have to take it with carefully. Okay. For all x not equal to 0. So, you want that function to be 0, except at the same time he wants this integral minus infinity to delta x dx to be 1. So, he wanted two properties to satisfy. It is a very important example and you should understand it properly. Okay. In fact, he wanted more. In fact, he wanted to be more. If f is continuous or f is smooth, continuity, differentiability, okay, he want to be require integral of minus infinity, of course let me write it, r f of x. So, you translate it at a point A. He wanted this to be f of a. That means he f will be your physical quantity. I will tell you little more about it because he is a physicist, or he has physical intuition, and then he wanted something. If it is, he wanted to even differentiate such a function. So, he wanted delta power k, if you differentiate x minus a, he want to recover the values of the your function or your physical quantities. He wanted this to be something like f power k of a. He wanted that to be that. Okay, maybe with a minus sign here, minus 1. So, let me remove it rightly. He wanted minus 1 power k. That is irrelevant now, you see. But let me call this to be 1, let me call this to be 2. So, but from a mathematical point of view, so this is the problem. If delta x not equal to 0, for all x not equal to 0, then except at one point your function is 0. Naturally, if delta is a function, this will imply integral of delta x dx is equal to 0. So, how do we get is equal to, it is equal to 0, you see, you think one. So, mathematicians, this looks like a bit of an absurd statement. One, you are looking for a function except at the 0, it is 0, and it the whole thing is there. So, but Dirac has his physical intuitions. So, he was not really looking for kind of a function, rather he was looking deltas operators. He had that one, that is what we the proper mathematical theory was not available, but then he was looking for how the action of delta on other quantities. That is precisely your 2. Number 2 are the delta at various points acting on your fx to produce your f of a, or the derivatives of delta. So, what is wrong in this one is, so the issue is that you know the physical quantities, the point is a mathematical concept. This is what I want to do. Point is a mathematical quantity, deltas are, all these quantities will be your physical functions. So, in an experiment or in a normal practice, you cannot act something at a point, you can only act functions in a neighborhood, and this is the concept. Slowly this concept is what we have to eventually grasp properly. So, that the physically when you deal with functions or any physical quantity, when I say that this is my temperature, which I will tell again, function fx at a point, and no experiment can be done to get that temperature at a point, rather it will be working on a neighborhood. So, basically Dirac was looking for how a unit force act at a point. So, naturally the unit force cannot act at a point, rather unit force only can act in a neighborhood of that. So, with this a mild, it looks like a mild, but the consequences will be much more difficult. So, can we do some kind of an approximation to delta with which is more closer to your experimental setup. So, and that is what we are going to do here. So, maybe in the next page we will do. So, what the experiment you are doing is that, so you are want that instead of looking for thing, you look for some small neighborhood, say minus epsilon to epsilon, and look for a function which is 0 here. So, that is which is 0 here. So, you are relaxing. So, you are looking for a function delta, say because of epsilon, let me call it delta epsilon, which is 0, in except that in an outside the neighborhood. So, that mod x greater than or equal to epsilon, and at the same time integral delta epsilon of x equal to 1. Can we have, so we are making a small approximation to delta instead of except at one point you are looking for a neighbor. This is precisely the modifiers introduced in our modifiers rho epsilon. So, let me change the word delta epsilon to rho epsilon. You have seen this one. So, you have already seen these modifiers, such functions exist. Okay. So, you can have, depending on epsilon, you can put a large value. So, you will have rho epsilon. This can be done in any dimension. So, you can have rho epsilon of x equal to 0 if mod x greater than or equal to epsilon, at the same time rho epsilon of x dx is equal to 1. You have a precise construction which we have already done in our thing. So, when epsilon becomes smaller and smaller, so if you look another epsilon here, so if you look another epsilon here, say here, then you want this area to be the same, then you have to go further peak and you have to do that. So, you see, so the area to keep it 1. So, if you look at this function delta epsilon, so you see this delta epsilon of x converges to 0, this is for all x not equal to 0. So, somehow delta epsilon or rho epsilon, let me use now the word u epsilon. So, you have your rho epsilon, this rho epsilon of x goes to 0 almost everywhere, except at one point in fact. So, this looks like close to delta, what we delta, close to delta, what we want it. But the issue is that can we pass to the limit? So, can we, and we also can we pass to the limit. So, you want that limit to happen. So, you have a function which is 0 except at one point. So, integral rho epsilon of x dx, this is equal to 1. So, does this can converge? No, right, because the limit is 0 almost everywhere, but then this you cannot pass to limit, you cannot pass to the limit under this integral sign. So, if you are looking for the convergence in the point wise sense and if you are trying to see rho epsilon is close to delta, you are getting delta except that point, but then the second condition which cannot satisfy because there does not exist any such functions which would do that one. Okay. So, we will see this more about this rho epsilons later, and we will see in what way, what we are going to say, in what way, what under what convergence rho epsilon may approximate delta, because delta can, so delta is sitting probably somewhere else. We have to understand this delta. So, for Dirac it was fine. So, Dirac knew, and because this unit forces acting in a neighborhood. So, you need to work with rho epsilons in that sense. So, this basically this understanding of all these is led to what are called the generalized functions and all that, and how the Sobolev space is introduced, but still lacking some strong mathematical foundation of these things. Okay. So, we will go to the next. So, we will now introduce formally, not really formally. So, I want to, again it is a motivation of weak derivative. So, we will do that. Formal things will come probably in the next class, motivation of weak derivative. So, you have seen the example, the necessity of studying these things. Now, you will see something else. So, here the one important thing before coming to that, you want to understand function in a different setup. I want to understand in view of the previous example, you have to view functions as just like Dirac delta, because the Dirac delta he was trying to understand not as functions rather as operator. So, understand functions as linear functionals, functions as linear functionals, and two important things I am going to introduce now here, functionals and what are called localization, these two concepts, localization. So, let me recall exactly what I think, that if Fx is a physical quantity, it's rather say for example, Fx represents a temperature, Fx is the temperature at x. What I am saying, that no experimental setup can produce the temperature at a point. Rather, if you have your equipment is better, you may be able to produce the temperature in a neighborhood of that point. So, what you are measuring is not really f of x, rather than you are producing an average in that neighborhood. I hope you follow that. So, instead of temperature at a point x, what you will be getting is when your equipment is very good, you will be taking the temperature and finding it average. That means, if you have a neighborhood x minus h to x plus h, you may be producing these quantities x minus h to x plus h, not f of x. So, you see f of t dt. This is the quantities available, not f of x. Probably with the average, if you want to calculate, you put 2h. So, this is nothing but 1 over 2h integral of f of into characteristic function of x minus h, x plus h. Okay. And so, these are the quantities you have to work with. So, the question is, does this quantity, does the average 1 over 2h f, the characteristic function of x minus h to x plus h, represent f x close enough? Can you have this close enough? You see. So, when h is small, when h is small, okay. So, the quantities experimentally available are this one, not f of x. But does this really give you f of it? Now, here is an exercise which you have done in your basic analysis course. This indeed converges to f of x if f is continuous. You see. So, if f is continuous, these quantities star here converges to f of x, f is continuous, as h tends to 0. So, it indeed represents. So, instead of taking this average quantities, you will be able to take f of x as an approximation, that is good enough. But suppose f is not continuous, then you cannot work with f of x, because that is not available. You have to work with these averages, you have to work with these averages. not work with your f of x function. Okay. So, now let me, so that is what we are doing with. So now one of the some of the issues is that this characteristic function x minus h x plus h is not continuous, even that not continuous. So, working with that is little more difficult. So, you have a this is basically localizes your function. You are basically by taking characteristic function x minus h to x plus h localizes your function in the neighborhoods, which we what exactly we want it. But localization can be done, this principle of localization can be done using smooth functions, and this is your another exercise which you are going to be. Suppose so we are going out of your point wise approximation. Okay. So, this is your point wise understanding of your function. So, suppose f is continuous, you want to do it. Okay. Suppose f is continuous. So, let me give you an exercise. F is continuous, and then integral of say from a to b. So, let us do it from a to b, continuous on a b, and integral of f of t phi of t equal, even without continuity you can get almost everywhere, and equal to 0 for all phi continuous and compact support. You may not need all this, I am trying to make as minimal class as possible, compact support. All these notions are already introduced. Okay. Then you can say that f identically 0. So, that means more generally this exactly means that instead of point wise, understanding, you can actually understand these quantities, integral of f, you see. So, because this is equivalent when f is continuous, but then this will be more general, which we are going to see that. So, more generally integral of a to b f phi equal to integral of where g is also continuous g phi, that implies f equal to g almost everything. What I am trying to see that you can recover your functions by understanding these quantities as an operation, that is okay, and this association is going to be linear, and where phi is for all phi in continuous functions with since that notations are already introduced these two. But you can relax little bit, you can actually take a smaller class. It is better to have a smaller class than a bigger class. You have to verify this association for all the phi in Cc of omega, but you can actually true. In fact, you can do this exercise a little more, and it is enough to consider C infinity function, enough to consider for all phi. This is a smaller class in Cc infinity of infinitely many differentiable functions with compact support. This is so to verify that one only for a smaller class. This is precisely your d omega class, which we have seen it already in Cc of omega. Okay. Cc of omega. Okay. So, you see, so you have another way of understanding your point wise approximation via the linear operations, and you don't have to restrict it to your characteristic functions, rather you can restrict it to this class of functions. So, there are a couple of points you have to understand. So, the compactness of phi basically gives you the localization. Okay. You can localize and you can understand, yeah, that I will tell you. For example, phi is in 4, you can locally understand that function. For if phi is in D of AB such that support of phi contained in CD, a smaller interval, and suppose that means you have AB here and you have CD here. So, we are considering this support here. Why this is called a localization? So, suppose this formula says that integral of f equal to 0, instead of for all phi in D of AB, I am taking for all phi in D of AB with support is a smaller class equal to 0 for such p, that implies f equal to 0 in CD, you see. So, locally you are that means you have two functions f and g such that f equal to g integral of g phi for all phi support in a small set, then you can say that. So, you can derive the information, the equality that locally. So, you can locally trying to recover the functions by acting functions on operators with support them. Okay. So, that is the thing you want to discuss it here. So, what else more you want to before going, maybe. Of course, instead of continuity here, you if you do not have the continuity of f, then you will be able to derive f equal to 0 almost everywhere. So, you can generalize such things. Okay. Okay, so let me do little more. And maybe one more example, let me do that. So, what finally I am telling that instead of viewing, this is the conclusion, instead of viewing x going to f of x point wise, and this is what the whole distribution theory you are going to see that. So, we are getting out of your point wise understanding, point wise we see, because which is equivalent you seen already, we see it as an operator, we see it as an operator phi going to integral of f of phi for all phi in d omega, you see. So, you have a different way of looking your function as an operator, and this gives you new objects which is soon to be seen here. So, maybe one more and this is one more comment, and then I will stop it this lecture. One comment, this is more important, this is more important, everything is important, this is more visible when you deal with the derivative, when we deal with derivatives. Okay. For example, let f be C1, C1 of AB. Okay. Then you have your point wise association, x going to f prime of x. But the whole motto was that get out of this pointwise approximation, view it as a an operator, view as operator, view as operator phi going to integral of a to b, maybe C1 to avoid any boundary problem at this stage. Let us take it a closed interval. A to b f prime phi. So, I am understanding f, rather I am trying to understand f prime as an operator. But then since phi is smooth, you can do an integration by parts, and phi has compact support. Since phi has compact support, support of phi is in AB, so you will have A to B f phi prime, because since boundary terms do not come, so that support of phi is contained in AB. Okay. So, what is this this integration by parts immediately tells you x going to f prime of x can be understood from, can be recovered, f prime recovered from phi going to, with this kind of integration, integral of a to b f phi prime. And what is this advantage? This can be defined even for non-differentiable functions. Though we started with a, so this can be defined, this can be defined, this association can be defined for non-differentiable functions, non-differentiable functions, you see. So, that gives you a window for us to define derivative in an operator sense, even if the function f is not differentiable. And this is what we are we will see some examples, and this produces new objects, because this association can be more general and every association may not be. So, yes, function if you have an association, but the association may not be given by a function, and that is a new object which you will see in the next class. Thank you.